Hello and welcome everyone. Very happy that we are all together again. In this tutorial, we will start talking about the electrical design of the lighting system. So fasten your belt and let's get started. The aim of this tutorial is to know how the electrical lighting system is designed by designing the wiring system for the lighting system. So we will know what are the different parameters of the lighting system, like the wiring design and the selection of the circuit breaker rating. So let's go ahead. If you remember, we said before that each electrical load is connected through the distribution panel, and the distribution panel is a panel like the panel in your home, which consists of the circuit breaker, and it has an ingoing circuit breaker like that one, and it has some outgoing circuit breakers like those ones. And each of those outgoing circuit breakers is used to feed some loads. So each circuit breaker is responsible for connecting the electrical power to those loads or disconnecting the power from those loads. And as the lighting luminaires are some electrical loads, so we connect each group of the luminaires to a circuit breaker or to one of the circuit breakers of those outgoing circuit breakers. And this line that is going out of the circuit breaker is the line wire. So it's connected through the luminaires from one terminal, but the distribution panel doesn't consist of the line only, as it has a busbar that consists of the neutral. So we connect a wire to the neutral busbar and we go out of this neutral busbar with this wire to be connected to the other terminal of the electrical luminaires. Hence, the lighting system takes its feeding system from the distribution panel through the line, which is connected to the circuit breaker, and the neutral, which is connected to the neutral busbar and the distribution port. But those line and neutral are not the two only wires connected to the luminaires we have, as we have another busbar in the distribution panel, which is called the earthing busbar or the earth busbar. And this earth busbar is used as a safety system, as it's connected to the body of the electrical loads to absorb any leakage of the electrical power which may lay on the body of the electrical equipment. Hence, we go out of the earthing busbar with a wire that is connected to the body of the luminaires we have. And finally, we find each group of loads to be connected with three wires. One from the circuit breaker, which is the line, and another one from the neutral busbar, which is the neutral wire, and a third one from the earthing busbar, which is the earth wire. And we call the wiring system of the group of loads that are connected to the same circuit breaker to be a circuit. So the same group of loads that is connected to the same circuit breaker with the three wires, the line, the neutral, and the earth, it's called a circuit. And according to this concept, we have a total number of circuits in the distribution panel that equals the number of the outgoing circuit breakers in the circuit. As each circuit breaker is corresponding to one circuit, so the total number of circuits in the distribution panel equals the number of outgoing circuit breakers in the panel. For example, if we have this distribution panel, which will be used totally as a lighting distribution panel, and it has, for example, 13 output circuit breakers, at that case we will have 13 circuits, as we have 13 circuit breakers. So 13 circuits will feed 13 groups of luminaires, as each circuit is responsible for feeding one group of luminaires. And each circuit of them consists of three wires, as we said, the line, the neutral, and the earth. This is because each group of luminaires needs three wires, the line, and the neutral, and the earth. Very good. Also, we can see the actual shape of the distribution panel to be like that one, where this is the ingoing circuit breaker, which is the master of the panel, or it's the master of all of the outgoing circuit breakers. And those are the three outgoing circuit breakers, which represents the circuits we have as we go with a line out of each one of them to feed a specific group of loads. And this is the earthing busbar, which is used for protecting the loads from any leakage of the electric current. So we can take a wire from the earthing busbar for each circuit, and it will be connected to the external body of the load. And finally, we have this is the neutral busbar, which we take a wire from for each circuit to be connected to the second terminal of the load to close the circuit. And each group of luminaires will be connected to one circuit, which consists of those three wires, the line, the neutral, and the earth. Alright, but you can ask now, what is the number of luminaires that each circuit consists of? So we need to know what is the capacity that each circuit can withstand. And here we say that we insert a number of circuits according to the total power of those luminaires, as each circuit must have a specific amount of power which it mustn't exceed, and according to the standard level, each circuit mustn't have a total power that is larger than 1200 volt ampere. So the maximum total power is 1200 volt ampere for each circuit. And we can detect the total number of luminaires required for each circuit according to the maximum power value. So we can say firstly that the complex power S equals the active power P over the power factor of the luminaires. So the total complex power of the total luminaires on the circuit will equal the total active power of those luminaires installed on this circuit over the power factor of those luminaires. But the total active power of the luminaires equals the number of luminaires we have on each circuit times the power of each single luminaire. And by that way, we can substitute in this equation to get the total maximum number of luminaires on each circuit, as we set the total complex power with 1200 volt ampere, and we set the power per each luminaire to P 100 watt. And this is a standard assumption for the power for each luminaire to P 100 watt. And we set the power factor of the luminaire to P 0.8. And by that way, we extract the number of luminaires to P 10 luminaires. So the maximum standard number of luminaires installed on each circuit equals 10 luminaires. Hence, we can conclude that the maximum value of the apparent power of each circuit or of each lighting circuit equals 1200 volt ampere, and the standard total number of luminaires required equals 10 luminaires, and according to those two pieces of information, we get the circuit wire's cross-sectional area to be 3 times 3 millimeters square, and the first three is for the three wires we have, the line, the neutral, and the earth that the circuit contains, and the second three is for the cross-sectional area of each of those three wires. And finally, we find the final piece of information is the circuit breaker rating to P 10 ampere. As the line is not connected directly, but it's connected through a circuit breaker, and at that case we get the standard circuit breaker rating to P 10 amperes. So the miniature circuit breaker rated current will be 10 amperes. And those are the four standard values we designed the lighting system circuit according to. Very good. Now you can ask, what if we have a number of luminaires which is connected to the same circuit with the same circuit breaker and they have a total power that is larger than 1200 volt ampere? As the previous calculations or the previous standards depends on having a total power of luminaires on the circuit which is smaller than 1200 volt ampere. So how can we make a lighting design in that case which exceeds 1200 volt ampere on each circuit? Here at that case we need to calculate the rated current that this circuit consumes, and the rated current at that case equals the total power of the total luminaires we have over the voltage level, which is 220 times the power factor of the luminaires, which is 0.8. So that's for the rated current. And after calculating the rated current, we need to calculate the circuit breaker current. And for the circuit breaker current, it's equal 1.25 times the rated current. Then, after calculating the circuit breaker current, we get the circuit breaker, which has the next standard value of current. So, suppose we calculated the circuit breaker current and we got it to be 19 amperes. At that case, we get the circuit breaker rating equals 20 ampere, which is the next standard value, which we can buy from the market. Now, after calculating the circuit breaker current, we need to get the cross-sectional area that will be used for this circuit. So we need to get the line wire cross-sectional area, the neutral wire cross-sectional area, and the earthing wire cross-sectional area. And for that, we enter the catalog of the manufacturing company of the wires, and we enter it by the circuit breaker rating. Then we get the cable cross-sectional area according to the circuit breaker rating. For example, we can use some wires from this manufacturing company which has this catalog, and we enter its catalog with the current value of the circuit breaker or the circuit breaker rating. And we get the 3 wires cross-sectional area from this column according to the circuit breaker rating. And by that way, we can design the electrical lighting system in case of the total power of the luminaires on the circuit is larger than 1200 volt ampere. More than great. So that's about this tutorial at which we learned how to make the lighting system design or the electrical design of the lighting system. Basically right now, thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we are all together again. In this tutorial we will continue talking about the electrical design of the lighting system. So fasten your belt and let's get started. The aim of this tutorial is to learn about some notes related to the electrical design of the lighting system. Hence, we can cover most of the ideas that we can face during our lighting design. So let's go ahead. The first note we have in this tutorial is that it's not recommended to connect different types of loads on the same circuit or on the lighting circuit. So if we connect, for example, 2 luminaires on a circuit of the distribution port, it's not recommended to connect other types of loads on the same circuit, like the motors, for example. And the reason is that the lighting loads are some static loads, and this means that they consume a fixed amount of current, so it's a stable type of loads as its rated current is constant, or it doesn't vary in its power that it consumes. While the motors, for example, are some dynamic loads, not static loads, and the dynamic loads means that it consumes a non-constant amount of power and current. And this means the motors in some cases may absorb a larger amount of current, and in some other cases it may absorb some smaller amount current values. And this makes the circuit to be an unstable one. So if we connect the motor which absorb a non-constant value of current on the same circuit of the luminaires which absorb a constant value of current, it may affect the amount of light that is going out of the luminaire. So the lighting system at that case may be an unstable one, as it will produce a non-stable amount of light. So for that reason we recommend connecting the lighting loads on a separate circuit which is isolated from the other dynamic loads. Very good. Now the next note is that it's recommended to connect the lighting loads of each room on a separate circuit. So if we have 3 rooms, for example, we can connect 2 rooms on a circuit and the 3rd room will be connected on a separate circuit. And by that way, 2 rooms will be controlled from a circuit breaker, and the 3rd room will be controlled from the 3rd circuit breaker. And we do so for the controlling operation to be a more accurate one. So suppose we need to turn off a single room lighting loads from its panel or from the distribution panel, here we can turn off its circuit breaker. But suppose all the rooms are connected at the same circuit. At that case, if we turn it off the lighting circuit breaker, all the rooms' lighting sources will be off at the same time, so this is a non-accurate controlling case. And the second reason of connecting each room on a single circuit is that suppose there is a failure in one circuit, like a fault case or a short circuit case for example, or like an overloading condition. Now if all of the rooms are connected on the same circuit, all the rooms will be dark as they are connected to one circuit. But if we isolate each room, or if we connect each single room on a single circuit breaker that is separate from the other one, at that case, if there is a fault on one room, all the other rooms will be on, while this room only will be off, or this faulty room will be off. So by that way we manage to decrease the fault case as much as possible, and this is the safety reason. Alright. Now the final note we have is that it's not recommended to connect more than 10 luminaires on the same circuit, even if the total power of the luminaires is less than 1200 volt ampere. So suppose we have 20 luminaires and each of them is rated 14 watts. In that case, if we calculated the total power of this circuit, it will be 20 luminaires times 14 watt over the power factor of 0.8. So it will be 350 volt ampere. And it's very obvious that 350 volt ampere is much smaller than the 1200 volt ampere of the maximum power of the circuit. But we don't recommend to connect this power of luminaires on the same circuit, or we recommend to have a maximum value of 10 luminaires per each circuit, and this is not to have a larger voltage drop on the circuit due to the larger length of the circuit. As when the number of luminaires increases on the same circuit, the total length of the circuit will increase, and when the total length increases, the total resistance of the wires will increase, so the total resistance of the wires which carries the current to the luminaires will increase. This is because the resistance is directly proportional to the length of the wire. And when the wire resistance increases, the voltage drop will increase, as the voltage drop equals the current times the resistance. So when the resistance increases, the voltage drop increases, as is directly proportional with the voltage also. So if there is a larger voltage drop, we may find the voltage that reaches the last luminaire to be about 200 volt only instead of the 220 volt. And the luminaires may not work, or it may produce a very weak illumination. This is because when the voltage increases, the lighting output of the luminaires decreases greatly. As the relation says that each 1% decrease in the voltage will produce a decrease in the lighting output of 3%. So the lighting decrease is 3 times the voltage decrease. Alright. Now the last note we have is that suppose we design the electrical lighting system for a building, but we didn't decide what will be the type of the luminaire which will be used, and we need to design the wiring calculation for this lighting system. So the problem now is that we don't know what is the power of each luminaire will be used. And in that case, we suppose each luminaire to have a power of 100 watt. So for the unknown luminaire's power, we make the design based on the assumption that the luminaire's rated power is 100 watt. More than great. So that's about this tutorial related to some notes related to the electrical lighting system design. Hope that's clear right now. Thank you for watching and see you next tutorials.